Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about equivalence relations. The very definition is an equivalence relation is a relation that is reflexive, symmetric, and transitive. We've already seen that the equal sign is an equivalence relation. It is reflexive, x equals x. It's symmetric. If A equals B, then B equals A. And it is transitive. If A equals B and B equals C, then A equals C. So equality is an equivalence relation. First, some general notation. Let's suppose fancy R is an equivalence relation. And let's also suppose that the ordered pair AB is an element of that relation. Then we write A is equivalent to B, and the tilde here will represent this notion of equivalence for equivalence relations more generally. I'm going to define a relation on Z cross Z. So it'll be a collection of subsets of Z cross Z such that A minus A is in the relation for all A and Z, and also A is in the relation for all A and Z. My question is, does this constitute an equivalence relation? First, let me note that we're saying here that A is equivalent to A, and also A is equivalent to minus A. Is this an equivalence relation? Well, this gives us that it's reflexive, now, suppose A is equivalent to B. Then either B is A or B is minus A because of our defining properties for this particular relation. If B is A, then we have A equivalent to A. This will be the same as B is equivalent to A, which is also A equivalent to A. Let's check out the case when B is minus A. So we're assuming A is equivalent to B, but we're going to look at the case B equals minus A. Then A is equivalent to minus A. Does it necessarily follow then that minus A is equivalent to A? And the answer is yes, because every pair of this form has to be in there. It means that negative A, negative A must also be an element of our relation, which means negative A is an element of this relation. So we see then that this equivalence relation is symmetric. I've already let the cat out of the bag. This will be an equivalence relation. We just need to show that it's transitive. So we're going to suppose that A is equivalent to B and B is equivalent to C. The question we have to decide is, does that mean that A is equivalent to C? Well, there are two cases. if B is equal to A, then A is equivalent to A, and A is equivalent to C, and therefore A is equivalent to C. So this case works if B is equal to A. Case 2 is B equals minus A, in which case we have A is equivalent to minus A, and minus A is equivalent to C. From here, there are two possibilities. Either C equals minus A, in which case we have minus A is equivalent to minus A, then we're trying to show that A is equivalent to minus A. But we already have that because B is minus A. So there's another possibility, but there's another possibility. We had C equals minus A, or C equals positive A. But if C equals A, what does that give you? But if C is equal to A, then we want to show that A is equivalent to A. But we already have that. But this is one of the defining properties of the relation. And so the proof is over. We also have the following notation. If AB is an element of a relation, we write A is related to B. There are various classical relations that you might be aware of. Less than, greater than, less than or equal to, greater than or equal to, and also just equals. These are all relations, and we can have A less than B, or A is greater than B, etc., etc. In the next example, I'm going to suppose fancy R is a relation, and A related to B will be defined by A minus B is an element of the set of rationals. The rational numbers. So an example might be the square root of 2 and the square root of 2 plus a half. If you subtract these, you'll get a rational number. So these two would be related by this relation here. The question that we have is this an equivalence relation? So we have to check whether this is reflexive, symmetric, and transitive. So we'll start with the reflexive part. A minus A is 0, and that is a rational number. Therefore, A is always related to A. That checks the reflexive property. What about the symmetric property? Let's suppose A is related to B. Then A minus B is an element of the set of rational numbers. But B minus A is the negative of A minus B, and taking the negative of a rational number still gives you a rational number. We deduce then that B is related to A, and so that gives us symmetry. We only have left to check the transitive property. So to check transitivity, we'll suppose A is related to B and B is related to C. Does that imply that A is related to C? Well, we have A minus B as an element of the set of rational numbers from here. From here we know that b minus c is an element of the set of rational numbers. If you add these two numbers, if you add two rational numbers, you get rational numbers. So a minus b plus b minus c will be an element of the set of rational numbers because the set of rational numbers is closed under addition. But this is a minus c. A minus c is a rational number implies then that a is related to c. And that's transitivity. So we have the reflexive property, symmetric property, and transitivity. That means from now on, a related to b is replaced by a is equivalent to b. In the integers, a equivalent to b mod m is an equivalence relation. Well, a is congruent to a mod m for any integer a. That's true. What does it mean for a to be equivalent to b mod m? It means that a minus b is equal to a constant times m, where the constant k is an integer. So the difference is an integer multiple of m. Well, a minus a is 0, which is 0 times m, and that gives you a is congruent to a mod m. So to check symmetry, suppose a is congruent to b mod m, which means that a minus b is equal to k times m for some k in the set of integers. This is times. So what happens if I reverse this? I'll get the negative. When you reverse a subtraction, you generate a minus sign, which means b minus a will be minus k times m, where negative k is still an element of the set of integers, which means that b is congruent to a mod m as well. That gives you symmetry. And so we check transitivity, where we assume a is equivalent to b mod m and b is congruent to c mod m. Does this necessarily imply that a is congruent to c mod m? Well, a minus b will be k1 times m, and b minus c is equal to k2 times m, where k1 and k2 are some integers. Well, what happens if we add these? If you add them, the b's will cancel, and we'll have k1 plus k2 times m, where k1 plus k2 is an element of the set of integers because the integers are closed under addition. Therefore, a is equivalent to c mod m. That completes the proof that the congruence mod m is an equivalence relation. Let a be a string of letters and let L of a be the length of the string. So for example, L of DOG will be 3. We're going to define a relation by looking at the set of all a comma b such that the length of a is equal to the length of b, the set of all strings that have the same length. The question I have is this an equivalence relation? Well, we have to check reflexivity, symmetry, and transitivity. Clearly, a is related to a because the length of A equals the length of A. That gives you reflexivity. If A is related to B, that implies the length of A is equal to the length of B. But equality of natural numbers is an equivalence relation, equal sign for natural numbers, which means L of B equals L of A, which implies then that B is related to A. So we have symmetry as well. We only need to check transitivity. So if A is related to B, and hence the length of A equals the length of B, and B is related to C, which means therefore that the length of B is equal to the length of C, then the length of A will be equal to the length of C, because the equal sign is an equivalence relation, and so we'll have transitivity there. And that implies A is related to C. We deduce then that R is an equivalence relation, and so we can now talk about A is equivalent to B if their lengths are the same. So you can see as an application of the last equivalence relation that dog is equivalent to cat, and cat is equivalent to rat, and therefore dog is equivalent to rat by transitivity. But dog is not equivalent to deer. Nope. This has length 4, this is length 3. They're not equivalent according to the equivalence relation of same lengths. Show that the absolute value of x minus y is less than 1 is not an equivalence relation. We're saying the distance between 2 points is less than 1. Well, surely it is reflexive, because x will be related to x. X minus x is 0, and that's less than 1. So x is related to x. It's also symmetric, because x related to y equals the absolute value of x minus y equals the absolute value of y minus x. So if the first one's less than 1, so will the second one be. Therefore, x related to y implies y is related to x. So if we're trying to show that this is not an equivalent relation, then we need to show that it is not transitive. But this should be pretty easy, because it's easy to see how you can have 2 points A and B that are less than 1 unit apart, and B and C less than 1 unit apart, but A and C not less than 1 unit apart. So all you have to do is come up with a counterexample. First of all, let's note that 3/4 is related to 0. And also, 0 is related to negative 3/4. The distance between 0 and 3/4 is less than 1. The distance between 0 and negative 3/4 is less than 1. However, 3/4 is not related to negative 3/4. 3/4 this way on the number line, 3/4 this way on the number line, gives us a total distance between these two of 1.5, which means it's not going to have a distance less than 1. So this is not true. Therefore, this relation is not transitive. Suppose that R, fancy R, is an equivalence relation on some set A. The equivalence class of some element in A is, first of all, it's denoted by the equivalence class relative to this relation, and it's defined to be the set of all elements of A such that A is equivalent to B, the set of everything equivalent to A. So for example, suppose we're talking about A is equivalent to B mod M, let's say mod 2. Then the equivalence class of 2 will be, under this relation, will be -4, -2, 0, 2, 4, and so on. It'll actually be an infinite number of elements in the set of integers, the integers being the set that we're dealing with here, and there are all these different things. They're all equivalent to 2 mod 2. 0 is congruent to 2 mod 2, 2 is congruent to 2, 4 is congruent to 2 mod 2, and so all of these are congruent to 2 mod 2, and therefore they're equivalent according to this equivalence relation. That's the equivalence class. What's the equivalence class of 1? That's going to have -1, 1, 3, and so on. Have -3 over here as well. These are all 2 units apart because it's mod 2. Everything that differs from 1 by a multiple of 2, an integer multiple of 2, will be in this equivalence class. You should also see that the equivalence class of 0, according to this relation, will be the same set as the equivalence class of 2. And that's also the same as the equivalence class of 4. These all generate the same thing. All you need is one representative element of the equivalence class to write down which equivalence class you're talking about. Next, a bit of notation. If you're dealing with A is congruent to B mod M, then the congruence class of some number A, mod M, will put a little subscript of M here, the modulus that you're using. A partition of a set A is a division of the set A into 2 or more non-empty disjoint subsets. So, in other words, if you have A is the union of A1 and A2, but A1 intersect A2 is empty, that means they're disjoint, then you can divide A into these 2 pieces. As a quick example, suppose A is the set 1, 2, 3, 4. Let's let A1 be the set 1, 2, A2 be the set 3, and A3 be the set 4. Then these are pairwise disjoint, and A is the union. And therefore, this is a partition. All we're trying to do is divide the set into disjoint pieces that add up to the whole. Let's look at a recent example. A is congruent to B mod 2. What are the equivalence class mod 2? What is the equivalence class mod 2 of 0? And how about the equivalence class of 1 mod 2? Note that if you take the union of these 2, you get the entire set of integers. So you can see then that this equivalence relation divides the set of integers into 2 equivalence classes that form a partition of the set of integers. We proceed with a theorem. Let R be an equivalence relation the following are equivalent. A is related to B. Part 2, the equivalence class of A is equal to the equivalence class of B, and maybe surprisingly, the equivalence class of A intersect the equivalence class of B is not empty. If they share something in common, it ends up they have to be equal as equivalence classes. So I'm going to write down this list over here. A related to B. The equivalence class of A equals the equivalence class of B, and 3. The equivalence class of A intersect the equivalence class of B isn't empty. We need to prove that these are equivalent, which means we have to show maybe that 1 implies 2, and 2 implies 3, and then 3 implies 1. Let's begin by showing 1 implies 2. Let A be related to B, which means then that A is equivalent to B because we're talking about an equivalence relation. Now, to prove that A equals B, we have to prove the equivalence class of A is a subset of the equivalence class of B, and this is what we want to show. The equivalence class of B is a subset of the equivalence class of A. The way to show equality between two sets is to show these two subset relationships. If C is an element of the equivalence class of A, then C is equivalent to A. We have A is equivalent to B, and that implies B is equivalent to C, which implies C is an element of the equivalence class of B. Therefore, the equivalence class of A is a subset of the equivalence class of B. But we have to show the relation goes the other way around. If C is an element of the equivalence class of B, then C is equivalent to B. Since A is equivalent to B, by transitivity we have C is equivalent to A. And that implies that C is an element of the equivalence class of A, and that implies that the equivalence class of B is a subset of the equivalence class of A. We deduce then that the two equivalence classes are equal sets. And so the first property, A related to B, does in fact imply that the equivalence classes of A and the equivalence class of B are equal. We'll next show that 2 implies 3. So we'll suppose that these equivalence classes are equal. Then the equivalence class of A intersect the equivalence class of B will be the equivalence class of A, and that's not empty because A is in there. We next need to show that 3 is related to one of these other ones, since we've already shown these two are equivalent. We will show that 3 implies 1. So we suppose only that the two equivalence classes have non-trivial intersection, that their intersection is not the empty set. So let C be an element of that intersection. Then A is equivalent to C, and also C is equivalent to B. It's in both of these equivalence classes, so it's equivalent to both. By transitivity, A is equivalent to B, which means A is related to B, And that completes the proof. Our next theorem states something that we have, in some sense, already observed. An equivalence relation partitions a set into disjoint equivalence classes. We saw this because when we're looking at A is congruent to B mod 2, we saw two equivalence classes. And these contained everything. If you took the union of these two, you get all integers. And yet their intersection is empty. So Z is partitioned into the union of these two equivalence classes, and those equivalence classes are disjoint. So in our proof, let's first say that since A is always an element of its own equivalence class, if we take the union over all elements of A of the equivalence classes, we have to get A. And each A is in its own equivalence class. So we'll get the entire set. The only question is, are the various equivalence classes also disjoint? Now, if you take two elements in A, the last theorem says either the equivalence classes are equal or the equivalence classes are disjoint. If they do have a non-empty intersection, then in fact they have to be equal, according to the last theorem. That was the surprising thing. Now every element belongs to an equivalence class. The entire set A is the union of all of the different equivalence classes, and equivalence classes are either equal or disjoint. And so the set of equivalence classes forms a partition of the set A into disjoint equivalence classes. As an example, 0 mod 3 is the set -3, 0, 3, and so on. The equivalence class of 1 mod 3 consists of these integers, and the equivalence class of 2 mod 3 are these. Notice that they're disjoint, and yet when you take the union of these, you get the entire set of integers.